Hi, class. I hope you're all doing well. We're going to top off this week's discussion of the habitability of planets by looking at two planets in our solar system that are in or just near the habitable zone. That is Venus and Earth. So both are excellent examples that we can study to try and understand how the properties of a planet influence the overall environment, the habitability that it might have for life. You'll remember last lecture we talked about how the properties of the star influence the habitability. So today we're going to focus on the planets. Okay, so we're having a little bit of a thunderstorm here in Chicago right now. So you'll hear a little bit of thunder in the background. You can see the storms rolling through there on the radar maps. And I've had a couple of power glitches. So this is multiple times now I've tried to record the lecture. So we'll see if we make it all the way through. So in the background behind me today is the surface map of Venus. Now, Venus is a completely clouded world. We don't have any pictures of the surface, not the way we do for Earth or Mars, because you can't see the surface. So everything that we know about the global topography of Venus has been discovered with radar. So these are high-resolution topographic maps of Venus made with radar. We had a radar mapping mission called Magellan that orbited Venus for several years and create complete maps for us. And what you'll notice about Venus is that just like Earth and just like Mars, it has really varied topography. Now we've color-coded this exactly the same way we color-code the Mars map. So the blue areas are low, and then the red and white areas are high, and that's all based on whatever the global average is where we'll call sea level on Venus. Venus doesn't have seas, so that's defined in the same way it is for Mars. And so the interesting thing about the surface is it's very young. That is to say, when we look around, we don't see that many impact craters. That's our kind of default, our default clue that a surface is young. So something in Venus's geologic history has been resurfacing it, because there's no reason that it shouldn't have impact craters like Mars does, and in fact like the Earth does as well in a few places. And in fact, Venus has them in a few places. Well, what we think is going on is we think Venus has a lot of volcanic activity. A lot of the structure that we see on the planet, a lot of the kind of large flowy type areas, a lot of the kind of mountainous areas, all look just like volcanoes on Earth do. And so that's very interesting, because when we start talking about Venus's climate, one of the things about Venus's climate and how it's got into its current state is related to its volcanic activity. Okay, so you'll notice if you go look up, all the geography on Venus is mapped. So the kind of two most prominent regions that you can see up here near the North Pole, this is called the Ishtar Terra. Okay, and the Maxwell Mountains kind of stretch down from there. And then this kind of large belt area over here near the equator is called the Aphrodite Terra. Okay, so if you go look up stuff on Venus, you can read a lot about volcanic activity and the geographic structure of Venus. Okay, so let's go ahead and start a few slides. We're going to focus our attention here on Venus for this first half of this lecture, and then for the next lecture, or next half of the lecture, we'll go talk about Earth. So, you know, at first glance, Venus and Earth look very similar. And in fact, their physical properties are very similar. They're similar in size, they're similar in composition. The only kind of real obvious difference between them is the fact that they are slightly different orbits. Venus is a little bit closer to the sun than the Earth. And you might at first blush think that, oh, well, that must be what's responsible for the climatic differences that we see between the two planets. But as you and I discussed early on, your kind of initial impressions and your initial guesses aren't always right. And in the context of Venus in particular, it has taken us a little while to figure out what the story is all about and kind of overcome those initial expectations, that cognitive dissonance that we might have by just looking at the physical properties and expecting that it should be similar to Earth. Okay, so what we'll do is we'll kind of talk about the global properties of Venus. We'll talk about what we think the main difference between the climate of Venus and the climate of Earth is. That's what we call the carbon cycle. And then we'll talk about the greenhouse effect, which is responsible for Venus's current condition today. Okay, so, you know, the observations of Venus are as old as the observations of any planet. They began as soon as we invented the telescope. And the difference between observing Venus with a telescope and observing other planets like Mars or the moon with a telescope is that you can't see the surface of Venus, okay? And so one of the kind of interesting things about the history of Venus is it's a good illustrative example of how we've learned to refine our scientific thinking. The development of the scientific approach and the basis of, of evidence that we now use for everything we do in science, whether it's astronomy or biomedicine or engineering or physics or chemistry, right? The standards of evidence have really grown and become more robust. That's why science is such a nice self-correcting mechanism for discovering knowledge. But this is kind of a metaphorical trope that describes the way scientific thinking used to go. It is not necessarily that far from the truth, because the things I'm about to tell you are certainly things that have always been thought about, or at least depicted with regard to Venus when you start thinking about artist depictions and speculations about what the surface of Venus might be like. But I like it a lot because I think it really illustrates and captures how robust the modern scientific method is. Okay, so, you know, the observations of Venus have always started right here. You look at Venus just like you look at any other world, and you can't see a darn thing. There's not a feature to be seen from a telescope on Earth when you look at Venus. And that's because Venus is covered with clouds, okay? So what did people do with that knowledge in the olden days? Well, we know about clouds. We've seen plenty of clouds on Earth. What are clouds made out of? Well, clouds are made of water. Of course they're made of water. What else could clouds be made out of? Well, if Venus is a completely clouded planet, it's completely covered in water clouds, well, then it must rain a lot. And if it rains so much on a completely cloud-covered planet, then clearly there must be a swamp on Venus. And it's the entire planet is a swamp. And swamps, of course, are full of vegetation and interesting possibilities for life. And of course, what we all know, and if you go find old pictures of speculations about Venus, you'll see pictures just like this one. On primordial Earth, when Earth was very wet and very hot, just like Venus is now, then, you know, there were dinosaurs living in the swamp. So probably the life on Venus is dinosaurs. Okay? Now, that seems completely absurd and silly to us today, okay, because we know better. Okay, but before we had refined our scientific thinking, before we really understood the diversity of what planetary environments could be like, before we understood how rare life might actually be, these are the sorts of speculations that went on, okay? But of course, we know today that Venus is not a wet world. We know there is not a swamp on the surface of Venus, and that definitely means there are not dinosaurs living on the surface of Venus, okay? So what is modern Venus like? Well, the person who really sparked the discovery of what modern Venus is like is our old friend, Frank Drake. So we encountered Frank very early on in this class when we talked about the Drake equation. We'll return to the Drake equation during the last week or two of class. But one of the things that Frank also did in his career, he did many things, he's a very good radio astronomer, is he did radio observations of Venus. And one of the things you'll remember we talked about last week was that when you look at any object, we talked about it with regard to stars, in different colors of light, and you measure how bright it is in those colors of light, you can determine what the temperature of that place is. And so Frank was doing this for Venus with radio waves. And when he measured the brightness of Venus in radio waves and worked out what the temperature of the planet was, he discovered that it had to be really hot. And more to the point, he discovered that it was the same temperature on both sides of Venus, both the day side that's close to the sun and the night side that's facing out to space. And so he knew that that implied there was something very weird about Venus, that it was hot and uniformly hot on every side. Okay, so that was in 1962. So there's the nature reference there for those of you who go look up old scientific papers. Okay, but his colleagues in the astronomy and physics community rapidly picked this up. This was an era where we were first beginning to understand what the greenhouse effect was all about, and it didn't take too long, about 8 years, before a couple of scientists, Rasool and de Berg, at the Goddard Center, took the ideas of greenhouse warming and took the observations of Venus, they put them together and talked about the Venusian atmosphere, which by that time we had discovered had carbon dioxide in it, and they worked out that it was the runaway greenhouse effect that could explain the uniform hot temperature of Venus. And you'll see that in this early analysis, they had decided that the surface temperature of Venus must in fact be somewhere around 700 Kelvin. And as we'll see in a few moments, that is very close to the actual measured value on the surface. Okay, so it all started with Frank making these observations. And this is how knowledge about the universe evolves. We have cherished beliefs, we have things that we think and things we think we know, but then we make new observations. We have to update what we think is going on, and that drives us to deeper aspects of our knowledge. Okay, and that's certainly been the case with Venus. So when you compare Venus and Earth together, as we've said, they're very similar worlds. They're very similar in size, radius, and density. And so that means they have very similar surface gravities. But what's different about them is the solar constant. Venus is a little closer to the sun than the Earth is. So if you use the expressions for the stellar constant that we talked about last time, you can compute how much more energy Venus receives from the sun than the Earth does. And you might assume that that's what causes Venus to be a lot warmer. But in fact, those studies that describe the greenhouse effect, you can show that if you were to just take the Earth and shift it closer to the sun, to where Venus is, it would definitely get warmer because it's getting more energy from the sun. That's absolutely true. Okay, but it wouldn't get as warm as Venus is. The surface temperature of Venus is 464 degrees centigrade. But if you were to shift the Earth to Venus's orbit and take the Earth's atmosphere and chemistry and let the sun beat on it, then the Earth would only rise to about 45 degrees centigrade. So there's a huge discrepancy there, 400 degrees Celsius, that we have to explain. So it can't just be the energy input from the sun, because the sun just isn't putting enough energy on Venus to account for the difference. Okay, so what is it? Well, it's this greenhouse effect. And the greenhouse effect is driven by the carbon on the planet. Now, again, just because they're similar in size, right, you might expect it, but it is true. If you look at the carbon budget, you count how much carbon is on Venus, and you count how much carbon is on Earth, they both have similar amounts of carbon. But the difference is, it seems like most of Venus's carbon budget is in its atmosphere. That's why it has a runaway greenhouse effect. But on Earth, it's not in our atmosphere. It's actually trapped in rocks, and it's dissolved in the water. Okay, so what's the difference? What causes the difference in the carbon distribution on the two planets? They have the same amount of carbon, they have the same composition, mass, density, size. What makes one so different than the other? Well, it's the water. Venus has almost no water at all. Okay, there's hydrated minerals, that sort of stuff, but its water supply is not like the water supply of the Earth. And in fact, we know on the Earth, the carbon is intimately tied into the water cycle. Okay, so let's talk about that. So this is called the carbon cycle. If you've been keeping up with the reading, then you've seen this before. It was in chapter 4 of the book, and so let's go back and review it. Now, the carbon cycle is a cycle. That means it kind of goes around in a big circle, and you can pick anywhere to start the cycle that you want to start and then follow it around. So I'm going to start with the clouds because the clouds are kind of the easiest place for me to imagine the starting. So Earth and Venus both have clouds. The difference is Earth's clouds are water clouds, okay? But on Earth, the clouds are water, and they will encounter geography, topography. They will condense and rain as a consequence of that. And that rain dissolves carbon dioxide that it encounters in the atmosphere into the water and carries it down to the surface. Okay, that water runs off to the seas, carrying the dissolved carbon dioxide to it. And then also as part of the running off to the sea is erosion, the weathering of the land. And so that breaks down the rocks and it carries minerals and other materials with it down into the oceans. Now in the ocean, those minerals and the dissolved carbon dioxide have plenty of time to react together. And so the chemistry works on each other. And so what happens is those chemical reactions produce carbonates, okay? And those carbonates settle out onto the bottom of the ocean as sediments, and they form carbonate-rich rocks. So the most famous one of these is limestone, called calcium carbonate. Okay, but what that does is it takes all that carbon that was dissolved in the water and it binds it and basically turns it into rocks. Okay, now on Earth, we have plate tectonics. Okay, and so at this point, geology takes over. All of the rocks on the plates will eventually find themselves in subduction zones. That's where the tectonic plates of the Earth come together. And those subduction zones drive those rocks down into the mantle where the rocks are melted. All of that carbonate minerals goes down and gets melted, and so that carbon becomes part of the mantle. The mantle, of course, circulates, and in places where it finds hot spots, it wells up to the surface again and forms volcanoes, and those volcanoes release the CO2 back into the atmosphere, and then the whole carbon cycle continues. Okay, so this is definitely a cycle, and it occurs on Earth, it occurred in the past, and it's still occurring today. Okay, now Venus at one point in its life almost certainly had water, okay, and it probably had a carbon cycle, but today it doesn't have any water. And so there's no water on Venus to drive the carbon cycle, which is why all of the volcanic activity has released and deposited that carbon dioxide into the atmosphere of Venus. Okay, so the question is, what happened to Venus's water? Okay, Venus and Earth are similar, and they probably, in all likelihood, had similar amounts of water to start with. They had to have, because the same process that delivered water to Earth had to have delivered water to Venus, volatiles coming in on icy bodies from the outer solar system. Okay, well, it's this slightly closer business that actually makes all the difference. If you took Venus and made it just like the primordial Earth, wet, lots of water, okay, and you push the primordial Earth a little bit closer to the sun, then the temperature would be about 45 degrees centigrade, as we said. The difference is, over the course of billions of years, that slightly warmer temperature causes the water to evaporate more readily. And so the oceans evaporate more than they do in the Earth's slightly larger orbit. Okay, so if the oceans evaporate more, there's more water vapor in the air. And like CO2, water vapor is a greenhouse gas. And so that drives the temperature up even more, which makes even more water evaporate. Okay, that's what we call a feedback cycle in climate. Okay, it's a positive reinforcement that takes a little effect and then it kind of makes it continue even more. So I often liken this to walking into your pantry and picking up the bag of Doritos, right? You eat one Dorito and it forces you to eat more, right? That's a feedback effect because it was so good, you had to eat another one. Well, this is the same thing. You evaporate a little bit of water. If you can't shed enough heat, then that makes it even warmer, which evaporates even more water, which prevents you from shedding more heat, and the cycle just kind of builds up. Okay, so climatic balance is a very delicate thing. So the consequence is that there's lots of water vapor in Venus's early atmosphere. Ultraviolet light breaks up water, and when it breaks up water, that allows the components to escape. The hydrogen escapes off to space so that you can't make more water with it. The oxygens that are left get bound up in the rocks through all the volcanic activity. Venus also, like Mars, has no magnetic field. So the Earth does have a magnetic field. Venus does not. That's because it's not rotating very fast. And so as a consequence, the solar wind also helps strip those light molecules out of the upper atmosphere, which is also something that happens on Mars. So Venus had a lot of things working against it. And in the end, that being a little slightly closer really kind of pushed it over the edge and drove it into its current state. Now, some books you read will put Venus inside the habitable zone. That depends on your optimism and what you think. But if you consider the actual properties of an Earth-like world, which is the way we defined the habitable zone last time, then an Earth-like world at the location of Venus would in fact become not habitable. So that's why Venus is outside the habitable zone in our solar system. So once the water vapor started building up, the carbon from the volcanoes was in the atmosphere. There was no carbon cycle to draw it back down into the rocks. And so you end up with lots of greenhouse gases, as we call them, in the atmosphere. So this is a very nice graphic. This is one of my favorite graphics that shows how the greenhouse effect works. This is one from Wikimedia. So if you go to Wikipedia and look this up, you'll see this graphic there. I'll show you a different one in the second half of lecture so you can just see the different kinds of graphics that people show for this. But what I like about this one is that it actually shows what's going on. So initially, energy from the sun in the form of visible light comes into the atmosphere and makes it to the surface, and then it warms up the surface. That's why, you know, your sidewalks and you know, your garden soil and everything feels warm when it's been sitting in the sun. That warm surfaces re-radiate the solar energy, not as visible light, but as infrared light. And so that is these big red arrows coming up from the surface. And infrared light very readily interacts with all of these molecules that are greenhouse gases. So you see carbon dioxide there, you see water vapor there, and you see methane there. Now, those molecules absorb that infrared radiation, but then they have to get rid of it. They don't like to hold on to it. And this is the point in the greenhouse effect. When they get rid of it, some of it goes out to space, but some of it gets re-radiated back to the Earth. Okay, if those greenhouse gas molecules weren't there, then all of the radiation would just go out to space. But it's the fact that these molecules intercept it, and then some of the energy they send back and some of the energy they send to space is what actually causes the greenhouse effect. Okay, so when a planet is balanced with the greenhouse effect, the overall incoming energy is balanced with what's trapped and what's going out. When you have a runaway greenhouse effect, the amount of energy going out is very small, and so it takes a long time for the temperature to rise up until it can push past all the molecules and radiate all of its energy out to Earth, off the planet. Okay, so we will come back to that discussion next half of the lecture when we talk about Earth. Okay, so Venus is an example of climate gone awry. Okay, and it's in fact one of the prime examples why we worry about the climate of the Earth, but it's an example of how our search for habitable planets is going to be dogged by the fact that the planet themselves can have tremendous effect on what the overall environment is like. Okay, so I hope you're all doing well. I hope you're staying safe, and I will talk to you again soon.